Welcome, EE123, lecture 30. Woo! See, I've recovered. Okay, today we're going to talk about tomography. But before this, just hot from B courses. So frequency correction frequency not correction challenge, but frequency estimation challenge. So the frequency was 144.279.242.33 hertz. Okay, so Nathan Wong, pretty close, up to 600 hertz. 600 hertz at a megahertz, a few megahertz. That's less than a ppm. I mean, yeah, less than a ppm. So it's pretty good. I don't know how they did it, but there's no. Okay, David, 3 kilohertz away. 3 kilohertz at 140 megahertz. That's 1 kilohertz. So it's 3 ppm off. Shane, okay, I don't know. Maybe just for the sake of it. And Richard, it's pretty good. 20 hertz away. Very good job, but quite a. Let me read the description. Sadly, not a contender for worse abuse of the rule, which would have involved using GPS discipline reference, which we weren't able to get locked, driving an arbitrary waveform generator and creating a precise 28.8 clock that fed into the RTL SDR. But this did involve massive amount of hardware, disassembling the RTL, leveling back side solder joint, and thermally attaching it to the metal plate. Also did as much as compute as possible with high sampling rates to improve FFT frequency, though ultimately there still remains about 0.2 jitter calibrating to the GSM base station. So assuming my isn't massively off, we should be within 2 ppm initially. So I don't get. Do you use the GPS or no, or it was just all the GSM?
It was I used the first one we tried to set up the base station that had a GPS lock frequency reference, except it was actually set up such that it said 24 volts into one of the LVDS lines, and we heard lots of sparks with smoke.
Oh, from the SDR?
No, from the timing reference. So apparently, what was that? No one could tell the LVDS line anyway.
Okay.
This submission was actually done just using the RTL SDR tool to the metal plate on the balcony of Soda.
Uh-huh.
I also did a second step where it did hook up the arbitrary wave generator.
So wait. So you got this by using the GSM base station, basically.
Yeah, using GSM.
So with no frequency reference other than that.
And the arbitrary waveform generator.
Oh, the arbitrary waveform generator.
So if you're on a solid crystal, you can hook the arbitrary waveform generator to the crystal instant, and that can like 2 ppm just without any compensation.
Okay. So it was fed directly into the RTL SDR to drive it. Okay, cool. Yeah. Kudos on the great work. That's quite a bit of effort. But it was using the RTL SDR, so I would say that counts somewhat. So I would say, how did Nathan? Nathan is here? No, he's not here. Okay. Well, I'll figure out how he did it. Otherwise, I would say number 1, but a little bit out of because it's not using GSM. And then, there was?
Yeah. I mean, we still have, even with the arbitrary waveform generator, I was going to expect the 1 ppm.
Oh, okay. All right. Well, number 1 then, and then number 2, and number 3. Good job. All of you get radios because there's just not that many submissions, and so just for the effort. Okay. All right. So, any questions?
What was like you were expecting to see in that competition? Like how close were you expecting?
I think you can do it. So the GPS base stations are spec to about 0.2 ppm or something, or 0.5 ppm. So you could do that. you could get out to 0.5 ppm, which is pretty good. Yeah. So that would be a reasonable rate. Okay. Any more questions before we move on? So the plan is after this class, after today, all the discussion section are becoming a lab batches. You're going to see there's going to be more work related to labs now and the projects. So feel free, we'll try to give you as much as exposure time with us during the next few weeks. So I'm also going to have some meetings with projects immediately after class. And then on Wednesday, by Wednesday, everybody should have seen me. Next, on Wednesday, we're going to talk about, this Wednesday, we're going to talk about Lab 5, the part of the communication. Next week on Monday, we have Laura Waller, who's going to give a talk about computational optics, which I think is really cool. And then that's pretty much so far as a special thing is going to happen. So try to make sure that you're here on Wednesday, those who are just listening, because we're going to give a lot of tips about Lab 5, which really requires a lot of details. Okay. So I want to talk now about, last time we talked about 2D. 2D is better than 1D because it's at least one more dimension to play with. And so there's interesting things that happen when you move to 2D. For example, we can look at, remember we talked about the delta function in 2D? So this is a delta function in 1D. And if you think of what is a delta function is actually defined as an integral. So when you integrate a function, multiply by a delta function, then it's really evaluating that function at 0. Okay? That's what it's doing. By definition, multiplying a delta function and integrating over it will perform this evaluation. So we'll give you a sample at x equals 0. Now in 2 dimensions, if you multiply with a delta function and integrate over the entire space, then you would get the evaluation of the 2D function at a particular point. Now this is a delta x, which is actually, this would be just so if you integrate, you'll get a single point if it's a 2D delta function. But if the delta function is just as a function of x, means that it varies in y, this is a delta line or an impulse line, then what it would do effectively is evaluate, now it's going to be a function of y, and it's basically evaluating a cross-section through this 2-dimensional function. Okay? So it's slightly different now. Okay? So yes, it is evaluating x equals 0, but now you've got a free variable, which is y. Okay? So it's a cross-section. Now if you do a double integral, so if you integrate also over y, then what you would get is in fact a 1D integral over this one-dimensional cross-section. Okay? So if I have a function, I make a cross-section, that's multiplying with a delta line, and then if I integrate over that, I would compute the area underneath that cross-section, which is a one-dimensional function. Okay, why do I even care? So let's look at a simple example. Here's a 2D function, which is, yes? Yes.
Maybe I'm forgetting my calculus, but should the last integral have a dx dy? Oh my god. Oh, I'm so close to money.
Right.
dx is flying above the integral.
Oh, yeah. Oh, it flew away. Oh. It doesn't matter.
Oh, yeah, sure.
There, interchangeable. Oh, look at that. Oh, my God. That's from last year, probably. Okay. Almost. I'll give you $1. Fine. Shut up. Last name? Is that your first dollar?
Yeah.
Oh, wow. C-H? C-H-A? A-L. $1. Good job. How many you have? $2? So now it's 3. Good job. Oh, so much money. Yeah, actually, it's a considerable sum. Last year it was $2, so I don't know why it is, because last year it was like $1 for each, and it wasn't that expensive, even though there was a lot of bugs. But now, I'm just keeping the same cost. Okay, let's move on. So this is a 2D function, and it's constant. So it's 1 underneath this parallelogram. Is that right? Yeah. It's 1 underneath that parallelogram, and it's 0 elsewhere. Okay, so it's parallelogram 2D something. Okay, so now I'm going to compute. I'm going to multiply it with an impulse line, and then I'm going to integrate over that. I'm going to multiply with this impulse line and then integrate over x, which in that case, f of xy times delta x. If I integrate over x, I would get f of 0 and y, which really would be just a rect of y. A rect of y, yes, because at this particular point, it goes from minus 5 to 5, hence, and then 1 from minus 5 to 5, which is really a rect function, okay, just by definition. So if I integrate over that entire space, then what I would get? If I integrate now over y, I would get 1, right? So if I integrate over y, then I integrate over this, and effectively I get 1 because the area underneath the rect is 1. Okay. All right, but now I can pick a different x. So multiply by a delta x minus x0, where x0 equals 1 in this case. So now I multiply by delta x minus 1. I integrate over it. I've got f1 comma y. So the function at x equals 1 and y, which will give me a rect of 2y. Because now my function is 1 from minus quarter to a quarter. Okay? And if I integrate over that, then I would get now 0.5, which is the area underneath this line. So now the question, what if I just integrate, what if I just compute a line integral? So this is what's called a line integral. Line integral means that I integrate over a line through a two-dimensional space function. And so the question, what about a general line integral with delta x minus u? Okay, so now u becomes a variable, so where I shift it becomes a variable. Okay. So in that case, now my result would be a function of u, which will be the shift of this delta of this delta line. So what's interesting about this is when I write this, so the function multiplied by delta x minus u, and then a double integral over that. This is a line integral For a particular u, it would be exactly the same as in this case. Right? For a particular u, for example, u equals 0, I will get 1. For u equal 1, u equals minus 1? Yes. Sorry, for u equal 1, I will get a quarter. A half. Okay. So now I have a situation where I have now a function, p of u, which is the line integral across the vertical direction. So in this case, p of u becomes a function. Okay, it's a function of u. And the function p of u looks like now a triangle. Because the line integral at this point is the highest, it's 1, and then it linearly goes down until it gets to 0 at this point. All right. So now, once I define this, then I can think of what is really a projection. If you think about this, this is kind of like shining light from one side of this two-dimensional object. It's kind of like weird, right? Because like let's say we lived in a two-dimensional world and all of us were flat, right? And I would put a screen behind this flat person. Then I will put a light shining through that person or cell or whatever. I will get the shadow, basically the one-dimensional shadow of that person. So this is really what we're looking at here. These are shadows. This is a shadow or a projection operation of this two-dimensional object. Okay, so shining light through and see basically what is the area. Why shadow would be a negative thing. Okay, but here in this case we kind of accumulate the result. But these are called projections. And so the question is, how would I describe now a general projection? Because I don't have to necessarily make a projection just from along the y-axis. I could perhaps make a projection along the x-axis, or I can make an arbitrary projection in an arbitrary angle. When I do that and define a general projection, now I'm going to have p of two variables. One is going to be how far are you from the center axis, and the other one is going to be what is the angle I'm going to be projecting at. Okay, so if this is the definition for a line for a projection across the y-axis, in that case, for a general projection, p of rho and theta, I can just write it as the integral, the two-dimensional integral over the function fxy multiply by a delta line that is that will be shifted along rho and rotated along theta. Okay, so this is just rotation of the axes. If theta was 0, let's see what would happen. If theta was 0, then I would get this to be 1, and this would be 0. And then I will get rho minus x, which is, I think, fine. Yes. It's just the negative of what we did before. Okay. And if theta was 90 degrees, then if theta was 90 degrees, then I would get exactly what I had before. If theta was 90 degrees, then this would be 1, and so I'll get rho minus y. And before we just had the situation where we had x minus u. Okay, so just reversing the sign, but it doesn't really matter. Okay, so this is a line now integral along throughout the object, where the angle theta is defined from here. Okay? The angle theta is defined from here. And actually, the reason what we got also a negative y is because we define now theta to be this way, and so the projections are going to be happening that way. Okay. So this is the line. This is the angle theta, and this is rho, where we are on the radial direction, effectively. Okay. And rho can either start from 0 over here and then go negative and positive, or it can be you can define a point where it is 0, and so on and so forth. Now, why is that even interesting? Because this is all related to, for example, projection X-ray. In projection X-ray, I shine X-ray through you. The body attenuates the X-ray energy, and it's captured at the back through either a film or a digital detector. And in fact, if you look at what how the attenuation actually works, the attenuation is you can think of it as exponential. So every part of your body exponentially decays, create an exponential decay, which is linear in the log. Okay? So it's linear in the log. Every part of you can model actually the attenuation as this part will decay by e to the minus something coefficients delta x, and then this part again by e to the minus coefficient again delta x, and so on and so forth, and it will be linear in the log. And so in the logarithm of the result is in fact the result of a line integral, okay, but in the log. But now you can think of the situation where you shine an X-ray through the body and you get this, which if you take the log would be a line integral, and then you get a single projection. Now this is a projection. Do you know what it is? What is a chest? And what is this part? The heart. What are these? So ribs, right? The spine, right? And what do you have here? What? Lungs, right? And what do you have here? Pneumonia. It's kind of hard to see because it's all overlaid on top of each other, right? So it's hard to separate. You really need to have a really large signal from the anatomy that you're interested in that will then be able to observe. For example, if there was a fracture in the bone, I would definitely be able to see it. But if there was something here in the spine, I don't know. It wouldn't be possible to see it at all. Okay, so what would we do? I probably will go and try to figure out from a different angle maybe, where it doesn't obscure, but sometimes there's just no way to tell.
Could you just crank
or is it?
X-rays too? Theoretically?
It's still it's all about contrast to noise ratio, right? And actually, the ability actually to measure any contrast. And so the question is whether it is generating contrast and how much you can see. And everything is overlaid on top of each other. It's really hard to say. And you can crank the X-ray up to a certain amount, but still you won't be able to see anything except that you would also cause damage to maybe get your patient some cancer.
Right.
Okay, some radiation therapy here.
Yeah, they probably complain about that.
Right. So the question is, can I look from a different angle, and probably I will get the same answer, or won't I? So what's a CAT scan really? CAT scan is a situation where I make a projection from one direction, right? And then I'm going to get one image, but then I'm going to look from different directions. And so if you look at the shadow of my fingers, then how do I know that these are actually two fingers or, four fingers, one after the other, right? I just don't know. But if I rotate, now there is, it can't be two fingers, right? Has to be something else. And then you go like this, and he goes like, okay, well, it can't be, Anyway, you can figure that out, that maybe you have enough information after you rotate it. It's pretty cool, huh? Okay, so the idea in a CAT scan, so it's the computerized tomography, is that you not only make one projection, but you'd make many, many projections. And the question is, can I recover the underlying anatomy or the underlying object by making projections through it? And the cool thing about it is that it turns out to be possible. And because it's possible, you don't have to actually probe the inside of this. You can actually probe it from the outside, and by making these projections, you can recover everything that's inside. And this is just an amazing result. So what they do is, this is a CT scanner, and this is a video from YouTube, where they open the CT scanner. They open the CT scanner, and this is the gantry that rotates. And it has a source, X-ray source, and it has detectors that make projections from different angles by performing these rotations at an insane amount of speed. This really is really heavy. And to think about the balance for this to rotate without vibrating, I mean, it's quite amazing engineering going on there. But the idea there is that I can make these type of images by putting a patient inside a CT scanner and then shooting X-ray at different directions, so making all of these projections, and then using a computer, I'm going to go and make those images, okay, from those measurements. So if you think about this, when we talk about compressive sampling, we said, let's move on from measurements, from sampling of the signal into making measurements. This is kind of that idea too. We're not making a measurement of a particular pixel, but a linear combination of many pixels throughout the body, right? So each measurement that we have is now a contribution of more. Okay. All right. So now this this projection, or the transformation from a 2D object into its projections at different angles and different offsets, is also called the Radon transform. Okay? And it's defined in this particular way. This is how you see it in the books. And so for a 0, theta, and rho, if you take this object, you'll make these type of projections, and then you would get you get this projection, and then if we rotate the angle at 0.4 pi, you'd get this projection, and now in this case you would get a rect function. Okay, right? Because this would be actually a rect function, right? The parallelogram. Okay. So the fact that now we have an object that looks like triangle for one side, and then a rect from the other side, and from all of these together, we can probably figure out then what is the shape. Now, the Radon transform is also called a sinogram. The reason it's called a sinogram is because it transforms impulses into sinusoids. Okay? Think about that. Let's say we have an impulse here at this position, and we make a projection. Then what will we get? We get a value at 0, right? Sorry. This is a two-dimensional space. This is rho and theta. Okay? This is not a graph. It's not a value, right? There's an intensity associated with it. Okay? So this is a two-dimensional function, and now I'm only going to have a value of 1 at rho equals 0, theta equals 0. Okay? When I make a projection in this direction. Right? So for theta equals 0, I'm going to get rho equals 0. Now I'm going to rotate it. And as I rotate, my rho, the position of this 1, the value 1, changes. And it will go till if I move 90 degrees, and now I make a projection here, then I'm going to get a value at rho that is positive. Okay, for y positive. And then as I move forward, once I get to 180 degrees, it's going to go back to 0. Okay, at rho equals 0. And then I move it again, and now I'm going to get a rho at y negative, and then again 0. So effectively, having a impulse at this position will give me a trace that looks like a sinusoid through this radon space. Okay? And this is what's interesting, because this transformation is linear. Every point here would transform into a different sinusoid with different amplitude and different phase. Okay? One cycle of a sinusoid with different amplitudes and different phase. If this was closer, then I would get if this was closer, how would my sinusoid look like? Just closer to 0. So the amplitude would now go down. So the amplitude will tell me how far I am along this axis. Okay? And what about if I move it over here? Or actually, let's move it to the x-axis. If I move it to the x-axis, what do I get? A change in phase. Okay? So where I am on the x-axis corresponds to the phase. Where I'm on the y-axis will correspond to the magnitude of the sinusoid. Okay? And a combination of these. So this is very interesting. Now this is not, you cannot write it as a sine of something, but it has a shape of a sinusoid, right? Okay. So in computed tomography, we have an X-ray source that shines X-ray through the body. And then I'm measuring the amount of X-ray that comes back. And through logarithmic relationship, I can get a result of a line integral, okay, that correspond to this line integrals. And so if I wanted to compute the sinogram through this object, it's going to look something like that. So this object is transformed into this signal. So this two-dimensional signal, its radon transform looks like that. And now the question is what does it take to take this and be able to compute back that? Okay? So just to invert that operation, or invert this radon transform, such that when I have a sinogram, I would like to get my object back. And the process of doing this is called filter back projection, and this is what we're going to talk in the next, the last 15 minutes. Yeah. So rho is where you are. Okay, so this is rho. This is rho negative, this is rho positive. And theta is the angle, right? Yeah.
We're just modifying theta. We're not doing rho.
No, but so you can think of a situation where you have like one source and one detector. And so you can, shine here and then scan rho. Here we do all the rows in parallel. Okay?
From the sinogram, rho is a cross and theta is top to bottom.
Yeah, rho is across and theta is top to bottom. Yeah, but you could, one of the early CT systems will have one detector, one source, and then you would just go and scan like this, and then rotate, and then scan and rotate, and obviously it's not efficient. So they added, like a array of detectors, okay? But then you don't do an array of sources, so I'll talk about that. This is called fan beam CT, and we'll get that just at the end, and see how that relates to. Okay. So it all comes down to the projection slice theorem by Bracewell. Okay? And this is a beautiful, beautiful theorem. And what's beautiful about it, that it's led to a Nobel Prize. That led to a Nobel Prize for CT, because it's all based on this particular theorem that originally actually was came about from the context of radio astronomy. Okay? It comes up in radio astronomy, where you do lots of Fourier imaging too. And the projection slice theorem says the following, and this is quite surprising, but yet, of course, in hindsight, it makes sense. It says the following: if you have a projection through the object, okay, so if I have P of rho and theta, so I made a projection. And then, so this is a one-dimensional signal. I'm going to take this one-dimensional Fourier transform of this one-dimensional signal. Okay. If I do that, as it turns out, computing a 1D Fourier transform on this one-dimensional signal will correspond, do you see the sign correction here? Yep. Okay. Will correspond to a cross-section through the two-dimensional Fourier transform of that object. You see what happened? Even my microphone was shocked. You have the 1D signal, I compute a 1D Fourier transform, and then that corresponds to a cross-section or a line through the two-dimensional Fourier transform of that object. Whoa! Mind-blowing, right? So the process is compute the projection. I get, in this case, is P of rho and 0. Okay, that's P of x. It's P of x, effectively. I compute a 1D Fourier transform. I get something. And then as it turns out, that corresponds actually to the Fourier transform at fx and 0. Okay? Which is the value of this, if you place that on top of this line, would be this cross-section of this two-dimensional Fourier transform. That is very interesting. It's very interesting because it tells me really what is the information that I have from a projection. Each projection gives me information that is really just one line in this Fourier transform. Fine. What if I want to collect the entire Fourier transform? What do? I go and make more projections, and more projections, and more projections, and each one of them gives me more information about the 2D Fourier transform. And then I can tell you, okay, I know how many I need. I need from all directions, obviously, because otherwise I'm going to have holes in the Fourier transform. And maybe you can even tell me, through sampling theory, of how close those projection needs to be on how many I need to make. Now we're only talking about continuous, right? Now everything is continuous. So rho and theta are all continuous. But when we go to discrete, we can then think of, how to sample. What does that mean? So if I rotate, now I get the projection along so I get a line across this. So people interchange this, like a 2D Fourier transform that is on a polar grid, they interchange that with projections. People will say, oh, this is projection, this is a projection type of acquisition. It's not, it's in the frequency domain, but they interchange that because they have this equivalency between a projection and a Fourier transform. And so if I make many, many projections, then I would get all around. So let's prove it. And I'm going to do the proof. It's a very simple proof. And I'm going to do it only for theta equals 0, because once we prove for theta equals 0, I can just rotate the grid, right? Because rotating the Fourier transform is exactly this. So rotating the grid, I can actually prove for any angle. Okay. All right. So how do you prove? You start with a projection. P of x is really the integral from minus infinity of infinity to mxy along dy. Right? So integrate over y. That gives me the projection that is P of x. If I integrate over y, then I get a function that relates to x. Okay. So that's good. I want to get back to that one. Okay. Remember this. So now I'm going to start with a line in the 2D Fourier transform at ky equals 0. Okay, so the spatial frequency y equals 0. If I'm going to write it, what is the 2D Fourier transform of this function? I write it down, double integral from minus infinity to infinity over y and x of my function times e to minus I to pi kx x plus ky y. Okay, so this is the 2D Fourier transform, but I know that ky equals 0. So I can erase ky. Okay, so now I just have kx, but a double integral over y and x. Okay, so now, because I have this double integral over y and x, I can first take the integral over y and then take the integral over x. So I can do this separate. So now I'm taking the integral over y. And then over that, the integral over x, and the integral over x has to be multiplied by e minus I to pi kx x. But wait a second. Wait a second. Do I recognize something? I do. What is this? What is this? It's in blue. Since it's blue, I'm going to look at something else that's blue over here. And I can see, oh my God, look at that. This is a projection. This is P of x. So I'm just going to write down it as P of x. And now I have integral over P of x, e minus I to pi kx, which is the 1D Fourier transform of my projection. Okay, QED. It's very simple, noble, like to be famous, right? Simple theorem that everybody in class here could prove that you can become famous for. Only Bracewell did that first. Okay. Any questions? Okay, so now, if you think about this, we have this two-dimensional Fourier transform, effectively, when we make these projections. Can we use that in order to perform the inverse Radon transform? Can we use that knowledge in order to do? And so now, if we have a 2D Fourier transform in the polar grid, I know that it's invertible because I have a measurement of the Fourier transform just in a different grid. All I need to do is compute the inverse Fourier transform on a polar grid. Right? That's all I need to do. This is exactly what we're going to do. And of course, there's going to be implication when you have something that is actually on a polar grid. We have to change variables back to Cartesian grid. And there we need to do something. When you change variables in an integral, you're going to have some factors that's going to account for that. Okay. And obviously, if you think about the density, of course, when we make all these projections in the origin of the frequency domain, it's much more dense, even though it's a continuous domain. The mapping is such that it's much more dense in the origin than it's outside in the higher frequencies. Okay, so now I want to go and try to show you how you go about in making a discrete reconstruction. So let's say now things will be discrete. How will we go about and do that? before we go to this completely discrete, I'm going to go for a partially discrete reconstruction. Okay? So let's now assume that we have a continuous angle theta and a discrete rho. Okay? So my rho, does this actually make sense physically? I would say absolutely, because if I have an array of detectors and an array of sources, those often will be discrete, whereas the angle is kind of like continuous, right? That's pretty physical. Okay, if I do that, then I have the projection P sub theta of n now, and I can compute the dTft to get P sub theta of k, small k goes from -half to half. Okay, so it's the same as omega, but omega goes from -pi to pi. I just like that nice representation here in this case. And then from this, I can place it into the two-dimensional dTft of that function. Okay? Two-dimensional dTft of that function at f, k sub x, and k sub y. Okay? So now this is a situation. And I have that along this axis. And then I can make for all angles, so now we have all possible angles. Okay, theta is continuous. Theta is continuous. Okay, so if theta is continuous, how do I then go about and do the reconstruction? If theta is continuous, I can just do a integral from -5 to 5, and then integral from -5 to 5 of my function e to the 2 pi j kx times n plus ky times m dkx dky, right? That's the inverse 2d 2dt ft. That's great. But this is not what I have. What I have really is data that's on a polar grid. So I need to change my my variables. Okay, so I'm going to switch into rho and theta. And now I have to integrate from theta goes from 0 to pi, and then rho goes -half to half. And of course, you can interchange that to rho go from 0 to half, and theta going from -pi to pi, but this is the choice that I made. But when I do that, I have to multiply by rho. Okay, how do you call this? I forget. I'm trying to. I've been like for the last 3 slides. I'm trying to remember the word for it, and I can't remember. No, it's the Jacobian. So this is the Jacobian. Okay, so rho is the Jacobian. So basically, if you want to do that, then if you want to do this inversion into a Cartesian coordinates, you have to multiply this data that you collected by rho. And this is called a rho filter. This is the name for it. It's called like this is a jargon that they use in CT or computed tomography, in tomography itself, that you have to multiply by a rho filter. Okay? So when you do that, you have to first multiply by a rho filter, and then you can compute this integral. So I have my data, I multiply by a rho filter, and then I can compute now this integral to get back my object. Okay? So I'm running out of time, and I don't really want to rush through too much through it. I'll just give you the essence of what we're going to do next, and we're going to talk about this on Wednesday. The essence of what we're going to do about next is the following. We're now going to make discrete angles. If we're going to make discrete angles, then now I've got discrete rho, discrete, and then discrete thetas. If I got rows in discrete thetas, now my integrals will become sums. Well, I still have to multiply by this row filter in order to compute this inverse. Okay? And so next time we're going to talk about the notion of back projection, the operation of back projection, the operation of filtered back projection, and how do we go about and computing the inverse of performing a reconstruction in discrete, in discrete, not time, but like discrete space. How do we compute this reconstruction? And talk about what really is the sampling requirements for the ability to recover an object using computed tomography. Okay? All right, next time.